confusing server rooms, right? But honestly, don't worry. I'm here to guide you through it. We're going to break down these abstract structures into clear, actionable steps so you can build a really solid foundation. Let's dive right in and make some sense of how data is truly built from the ground up.
To keep us right on track, here's our roadmap for today. We'll cover the three-level architecture, dive into tools for data modeling, compare schema versus instance, open up the data dictionary, and finally, look at achieving data independence.
First up on our roadmap, Section 1, the three-level architecture, zooming in.
Think of this whole topic like a top-down journey. We're going to start right at the surface, looking at what you and I, the everyday users, actually see, and then we're zooming all the way down, layer by layer. So, the fundamental question to spark our curiosity here is, what are the three levels of database architecture, and honestly, why do we even need them? I mean, imagine if every single time you open an app, you had to manually tell your hard drive exactly where to spin and which sector to read. It would be absolute chaos. A database solves this by separating that clean user interface from the incredibly complex wiring underneath.
We actually achieve that separation using what's called the three-level ANSI Spark architecture. It's broken down into three specific tiers: the external view, the conceptual view, and the internal view. Just keep this mental model in mind as we step down these stairs one by one.
Let's step onto that first layer. The external level, or the view level, is essentially the user's view. And what's really fascinating here is just how highly customized this level actually is. It only describes the part of the database that's relevant to a specific user. It completely hides all the messy details and, really importantly, any unauthorized data. For instance, it might hide a salary field for security. It can even derive new attributes on the fly, like it can calculate your exact age right from your date of birth, without actually needing to store your age permanently. It also defines security levels, so it allows one user to, say, update an employee file, while another person only gets read-only access. It's essentially a perfectly tailored, completely secure window.
Now, stepping down one layer deeper, we hit the conceptual view. While that external view was for individual users, the conceptual view is the community view. It defines the logical structure for the entire database. This is where we describe exactly what data is stored and the relationships between all that data. We're defining data types, field sizes, primary keys, and foreign keys right here. But the absolute crucial point you need to remember: this level is entirely independent of physical storage considerations. It literally doesn't care what kind of hard drive you're using. It only cares about the pure logic of the data.
Finally, we zoom all the way down into the bare metal, the internal view, or physical level. This is the actual physical representation of the database on the computer. This level describes exactly how the data is stored. We're talking record formats, file structures, and indexes. It deals with the actual disk drives and physical addresses. Because it's just so highly technical and hardware-specific, designing the database at this physical level is the strict responsibility of the database administrator, or DBA.
Okay, moving right along to Section 2, Tools for Data Modeling, Building the Blueprint.
So now that we understand the three levels of architecture, we have to ask, how do we actually design them? What are the actionable steps a designer actually takes? Well, that brings us to data modeling. Business analysts typically start with the conceptual model. It's super high level. It identifies entities and relationships, but there are no attributes or primary keys specified just yet. Then they refine that into a logical model. This is where we get detailed. All the attributes, primary keys, and foreign keys are specified, and the data is normalized. But keep in mind, both of these first two models are still entirely independent of the target software or hardware. Finally, the database designer takes over to produce the physical model. This represents exactly how the model is going to be built in the actual target database management system, detailing table structures, constraints, and specific access methods. It's a really perfect progression, right from abstract business needs straight down to technical reality.
Next up, Section 3, Schema versus Instance, the variable analogy.
Let's tackle two terms that constantly trip up beginners. A database schema is the description or the layout of the database. You'll usually see it described using SQL create statements, and importantly, it's not expected to change very often. It's kind of like the permanent blueprint of a house. On the flip side, we have the instance. The instance is the actual data residing inside the database at any particular time. You might hear people call it the database state or a snapshot. Unlike the schema, the instance changes constantly, literally every single time you insert, update, or delete a record. So you can have many different instances existing over time for the exact same database schema. And here is an analogy that really makes this click, especially if you've done a little bit of programming. A schema is exactly like a variable's data type. Think about declaring a variable as an integer. That rule rarely ever changes. The instance, however, is like the variable's actual value, like the number 5 or 100 stored inside of it, which can obviously change all the time. Once you lock that analogy in your mind, I promise you will never confuse schema and instance again.
All right, moving into Section 4, the data dictionary, the brain of the database.
To look behind the curtain and see what keeps all these schemas and levels functioning so smoothly, we really need to understand the data dictionary. And that starts with metadata. The absolutely crucial point here is this. Metadata is quite simply data about data. It doesn't contain your actual user data. There are no customer names or product prices here. Instead, it contains all the essential bookkeeping information that's required for managing the database itself.
So what exactly is hiding inside this dictionary? Well, it consists of the basic definitions and organization of the whole database. It holds a master list of all the files and the number of records in each one. It tracks the names and the types of every single field, the relationships between data items, and all the indexes used for quick access. Most systems actually keep this dictionary totally hidden from everyday users to prevent any accidental destruction. And here's the really fascinating part. Without this data dictionary, a database management system simply cannot access any data. It would be completely lost.
And that brings us to our final stop, Section 5, Achieving Data Independence, Why This Matters. You might be wondering, why go through all this trouble? Why overcomplicate things with all these separated layers? Well, the answer is data independence. Data independence is the capacity to change the schema at one level of the database system without affecting the schema at the next higher level. This is pretty much the holy grail of system design. It means you have the power to renovate or upgrade one specific part of your database without having to tear down the entire system and rewrite all your applications from scratch.
Let's break this down into its two distinct forms. First up is logical data independence. This is your capacity to change the conceptual schema, like say adding new entities or attributes, without having to change the existing external schemas or rewrite the application programs that your users rely on. Second, we have physical data independence. This is the capacity to change the internal schema, like swapping out your storage media from clunky old hard drives to blazing fast solid-state drives, or changing how files are organized, without altering the conceptual schema at all. Your logical rules stay totally safe and insulated from any underlying physical hardware changes.
And this brings us right to our golden rule for today, which perfectly summarizes everything we've just learned. Upper levels are unaffected by changes to lower levels. This single, powerful principle is really what makes modern computing possible. I want to leave you with this final thought. Imagine, just for a second, trying to redesign a massive global database, like Amazon's or Netflix's, if every tiny hardware upgrade or every single new data field caused the entire user application to just break. It would be literally impossible to innovate. By separating the user view, the logical rules, and the physical disks, we create systems that can grow and evolve forever. Review these foundational steps from Lesson 1, keep them fresh in your mind, and I will see you right back here in our next explainer.